For many of the topics that we'll be covering in this class, it's going to be handy to talk about collections of objects. And in this and the next lecture, we'll be introducing the two main types of collections we'll be considering, lists and sets. Both lists and sets allow us, broadly, to talk about collections of things, but in different cases we will want to talk about different properties of those collections, and so we have two different types of collection that allow us to focus on different aspects. The fundamental distinction between a list and a set is that a list is an ordered collection of elements, and a list can have the same element repeated multiple times, whereas a set is an unordered collection of elements, and each element in a set must be unique. This definition of a list as an ordered sequence of objects is deliberately very vague to allow us to talk about lots of different kinds of lists. And so there are tons of wildly disparate things that meet this general definition of a list. Often we'll talk about lists that contain sequences of numbers, but we could also have lists of letters or of Boolean values or variables or concepts. And the objects in our lists could be things like Davidson classes. All of our lists have an ordering, but that may or may not be a sorted ordering, and the elements in our lists may or may not be unique. We'll often want to talk about the length of a list, which is defined in the obvious way. Using the concept of length, we can define a few other things that we'll encounter frequently. So any list of length 2 can be called an ordered pair, and a list of length 0 is the empty list. And we use a definite article here because all empty lists are, in an important sense, the same empty list. And so we can talk about what it means for two lists to be equal. So we consider two lists to be equal if they contain the same elements in the same order, which means that they would also have the same length. And since empty lists have no elements, all empty lists are equal to one another. Much of the value of lists over the course of the semester will come from defining particular lists for particular uses, but there are some things that we can do with lists in the abstract, such as counting the number of lists that have certain properties. If we want to count all of the lists with a certain property, it often helps to think about, either concretely or in the abstract, how we would write down all of the lists that satisfy that property. And we could write those lists down in an organized way by having all of the lists that start with T in one row and all of the lists that start with F in another row. And that naturally leads us to having all of the lists that end with T in one column and all of the lists that end with F in another column. And so here we have exhaustively written down all of the possible lists that contain only T and F. And so the answer to our question of how many of these lists do we have is 4. And this example may seem trivial, but we can use the same kind of organization to answer other questions. If we want to count all of the lists where the first element is a letter and the second element is a digit, then we could again lay them out in a grid where the first element determines the row and the second element determines the column. And so even though we haven't written down every possible list of this description, we know that this grid describes all of the possible lists because we have every combination of a possible letter for the first element and digit for the second element. And so we can use the size of this grid to count the number of possibilities. We know that we have 26 letters and 10 digits. And so we know that if we were to fill in this entire grid, all 26 rows and 10 columns, then we would have 26 by 10, or 260 total lists. So for counting ordered pairs, we can conceptually draw this grid where the number of rows is the number of possibilities for the first element, and the number of columns is the number of possibilities for the second element. And so the total number of lists is the product of the number of possibilities for the first element and the number of possibilities for the second. So if we generalize this to ordered pairs with n options for the first element, then our grid would have n rows. And if we have m options for the second element, then we would have m columns. And so we would have n times m possible ordered pairs with these constraints. So this is great for counting ordered pairs. But if we want to count the number of possible lists of length more than 2, then we can break the problem down into problems that look like counting lists of length 2. So if we're counting the number of lists of length 3 that have these constraints, we could break that down into first counting all of the lists of length 2 that meet these constraints, and then for each of those lists of length 2, consider adding each of the possible options for the third element. So we could exhaustively write down all of the possible lists of length 3 by drawing a grid where the height of that grid is n times m, where here we go through all of the things that we would have written down in the n by m grid for counting the first two elements, and then in the columns we write down the options for the third element, and so we end up with the product of the number of options for the first element, the second element, and the third element as our total number of possibilities for the length 3 list. And this pattern continues to generalize. We can figure out the number of lists of a given length by figuring out the number of possibilities for the first element, multiplying that by the number of possibilities for the second element, and so on through all of the elements up to that given length. This is an example of an inductive argument, and will formalize the idea of proof by induction later in the semester. We can also use our approach to counting the number of possible lists to answer questions like how many ways can we assign medical students to residency programs. We could solve this problem by making a list of the hospital to which each medical student is assigned, and then counting the number of possible lists. So our lists will have an element for each of the medical students, and so we will have lists of length 55. And for the first position in the list, we have 65 different hospitals that we could write in that position to assign to the first medical student. Then for the second medical student, we can assign them to any of the hospitals except for the one that we assigned to the first medical student. So we have 64 remaining options for the second. For the third medical student, we'll have 63 remaining options, and so on until we get to the last medical student, for whom we will have taken up 54 of the options already with the previous assignments, and so we will have 11 remaining hospitals to choose from. So there will be 11 options for the last element of this list. And so the number of lists with these constraints is 65 times 64 times 63, and so on, times 11. We can also write this using product notation, which is similar to summation notation. We use a pi symbol, and we are taking the product from I equals 11 to 65 of I. We can also count lists with other sorts of constraints, like having no repeated letters appear consecutively in a string. If we're counting strings of length 5, then we will have 5 elements. And for the first letter in the list, we have 26 possibilities. Then for the second letter, our constraint that there are no consecutive repeats ensures that this letter can't be the same as the previous one. So there are only 25 options for this element. For our next element, we have 26 possible letters, but it can't be the same as the previous one. So again, we have 25 options. And similarly, for the last two elements, we have 25 options. And so our number of length 5 strings with no consecutive repeats is 26 times 25 to the 4th. We could also answer questions about the number of possible arrangements of a collection. For example, the books behind me on the bookshelf when we're in class. I have 17 books behind me, and so we could answer how many different ways could I possibly arrange those books. Well, each arrangement of books corresponds to a list that gives the order in which the books appear, and so we are counting lists of length 17. And for my first book, I could put any of the 17 books there. And for the next one, I could put any book but the one that's already there. So I have 16 options remaining. Then I have 15 options for the third book, and so on, all the way down to the very last book. I only have one left, and so there's only one option remaining. And so the total number of orderings is the product of my options for each position. We could write this in product notation. And for this special case, where we are taking a product from an integer decreasing by 1 every time, all the way down to 1, this has the special name of factorial, which we denote with an exclamation point. So n factorial is the product of all of the integers from 1 up to n. And so at this point, the book devotes an entire section to defining the value of 0 factorial. We could just state this and leave it at that. This is a definition. But the book is right. This can definitely be unintuitive, and so it's worth talking for a moment about why. And in fact, there are a lot of reasons coming from a lot of different areas of math why it is convenient to define 0 factorial to be 1. But one line of reasoning that I think can be particularly helpful for computer scientists is thinking of the connection between factorial and the product of a list of numbers. If you were going to write code that takes in an array of numbers and computes the product of all of the elements in that array, your pseudocode might look something like this. This pseudocode loops through all of the elements in the array, and for each element updates a running product, multiplying it by that element, and eventually returning the result. And by initializing our intermediate product variable to 1, we ensure that as we go through the elements in the list, we always have a correct product of all of the elements so far. And that means that if we were to call this function on an array of length 0, then we would get a return value of 1, because the product of all of the elements in a length 0 list performs no multiplications, and what we return is just our starting value, which was the neutral element for multiplication. And we can think of n factorial as calling a product function on a list with the elements 1 to n. So we can think of n factorial as a product on the list of 1 through n. And so 0 factorial is the product from 1 up to 0 of the elements I, but this product has no elements, and so it's like calling our product function on an empty list. And so our product from I equals 1 up to 0 is a product of an empty list, and so it makes sense that that product of an empty list gives us 1. To help us in solving a wider range of counting problems, I wanted to go over a few additional techniques that are all based on the list counting we've done so far, but will be helpful in some special cases. If we want to count the number of ways that we can rearrange the 8 letters in the word wildcats, then we know that there are 8 possibilities for the first letter times 7 for the second, and so on, so we get 8 factorial possible arrangements. But if instead we have a set of letters that includes some repeated letters, like the 2 D's in Davidson, then there are fewer total possibilities because 8 factorial counts the 2 D's separately. If we index them as D sub 1 and D sub 2, then among the 8 factorial arrangements will be these ones. But these aren't actually distinct orderings of the original letters. And in fact, for any of the 8 factorial arrangements, there is a pair like this, where the only difference is that D1 and D2 have been swapped, so we have overcounted by a factor of 2. And the general technique here is that we can take the factorial number of arrangements total and divide out the sub-arrangements of the repeated letters. So if we had 3 D's, then there would be 3 factorial ways to arrange them, and we would need to divide the total by 3 factorial. We'll also encounter some counting problems where it can be helpful to split them up into mutually exclusive cases that we can count separately and then add up. If we're trying to count the number of length 2 lists we can make out of these letters by multiplying the possibilities for the first letter by the possibilities for the second letter, then depending on what gets picked as the first letter, we have a different number of possibilities for the second letter. If we first pick a D, then there are 7 possibilities remaining for the second letter, but if we first pick a letter other than D, then there are only 6 distinct possibilities for the second. So the number of lists where we first pick a D and then pick one of the other letters is we have 1 option for the first letter and then 7 options for the second. And if we pick something other than a D first, then there are 6 possibilities for the first letter, after which we exclude whatever was picked, and we have 6 possibilities for the second. And since we counted these separate mutually exclusive cases of either there's a D first or there's something other than a D first, we can add up all of the lists of this type plus the lists of this type to get the total number of possible lists. And a third approach that is related to each of these is to subtract from the total a subset that doesn't meet our criteria. Here, if we are making length 4 lists out of these 3 letters, and repeats are allowed, then we have 3 possibilities for the first letter, then 3 possibilities for the second, and so on. So there are 3 to the 4th total lists. And if we want to ensure that we are only counting the lists that have at least one D, then the most convenient way to do that might be to subtract the number of lists that don't have at least one D. Those are the lists that only contain A's and V's, and so we have 2 possibilities for the first letter times 2 possibilities for the second, for a total of 2 to the 4th. For all of these examples, the numbers we were working with were small enough that I could actually do the arithmetic to give you the answer. But a lot of times, if the lists we are counting are particularly large, it's really not worth it to do the arithmetic. And so in general, I am totally happy for you to give me an answer of the form 3 to the 4th minus 2 to the 4th, or 8 factorial over 2, rather than actually calculating the numerical value.